Okay, let's get started. I think we're quite ahead of schedule, so we'll probably just finish the stuff and end early today. Okay, and yeah, once again, the midterm should be in 1 week, so next week this time. And yeah, I should figure out the detail today later, and if I give you a formal announcement on e-learn. Okay, and okay, so any questions so far? And also because of midterm, so this week we will have no homework out. Okay, so you can prepare for the homework. but there is some stuff left over on chapter 3. So I think I will do some of it as example on Wednesday. So Wednesday we'll have kind of a midterm review. Okay. And today we're finishing on section 6. No, sorry, chapter 3, and yeah, we'll finish chapter 3 and probably just let us go back early. Okay, so let's go back to this theorem 3.6.6 again. So this is the main theorem about this about this action, and it says that the rank actually equal to the dimension of a column space. Okay. So we define the rank as dimension of a row space, and we prove that dimension of a column space also equal to dimension of row space. So rank of A equal to rank of N transpose, and it's really symmetric between between row and columns. Okay, and so let's see this once again. We have that. So we have two steps. First is the dimension of the column space. We prove that it's greater or equal to the dimension of row space. And on the second step, we just use symmetry to prove the dimension of column space equal to dimension of row space. So the hard part is the first one. So how do we prove the dimension of column space equal to dimension of row space? Is we go through four matrices. So first we have A. And okay, so it's maybe let's go to an example. Okay, so we start with our matrix A, and as usual, we do Gaussian elimination to get the reduced row echelon form U. Okay, so U is the reduced row echelon form of A, and then we find this interesting matrix that's UL and AL. So UL is a quite simple matrix. Is you look at the lead variable in U, so it's this one here and this one here, and well, you have some lead variables, and then you pick out its columns. Okay, and so for example here you pick out the lead variable here, and you get UL equal to 1 0 0 0 0 1 0, and so obviously those two columns are linearly independent just because how the reduced row echelon form should look like. It has like one somewhere. And so those are basically standard base. These are going to be standard basis elements, standard basis vectors. So obviously it's going to have color independent each other. Okay, and so that's UL is picking out the lead variable columns of the lead variables of U, and then we define this funny AL. Is you look at which columns you pick out from UL to get the UL, and you pick the same column in A. Okay. So here you see I pick the first column and the third column, so I also pick the first column and the third column in A. Okay, so I can form a matrix as AL here. Okay, so first step is we define this UL and AL. So you do Gaussian elimination, and you pick out columns in UL, and you pick out columns in AL. Okay, and then there is this interesting thing we can derive. And so first one already state. So UL is linear, has columns linearly independent of each other, just because it's obvious they have this obviously linear independent form. And then we know that AL is also linear independent of each other, and this is something. Maybe I should write it here again. Okay. So this is something that we state last time, but we can state again, because because U can be getting from doing all the reversible row operations from A. So we will have that. Okay. So we know that ax equal to 0 if only if ux equal to 0, because u is what should I write? Because u is equal to some e of a, where e is reversible, right? Because e is is a product of a elementary matrix. Oh, sorry, not reversible. We call it invertible. Wait, is it invertible? Anyway, e is non-singular. Okay. And okay, so the important thing here is AO is linear independent. Okay. And then we can have this chain of argument here. Okay. So dimension of the okay. So the dimension of the row space of A equal to, so this is the rank. And as a derivation before, we know that this is the number of rows in number of non-zero rows in U, because doing this because the row space of U equal to the row space of A, and obviously those two rows are linear independent. So the number of rows will just will be a dimension of row space here, and that will be equal to the dimension of row space here. Okay, and then here the number of non-zero rows obviously equal to the number of lead variable. So number of those 1 here is also equal to 2. And the number of lead variable will equal to the number of columns in UL, because, well, by construction, each lead variable will pick out a column. So number of lead variable equal to number of columns. Okay, so number of columns in UL also by construction equal to number of columns in AL. And then finally we use the thing that we say here. So the columns column vectors of AL is linear independent, because column vectors in UL is also linear independent. Okay, and so we have we have two vectors here that are linear independent, and we know they span a two-dimensional space. Okay, so yeah, so because those vectors are linear independent, so they form a basis for whatever space they span. Okay, and so the dimension of the space spanned by those two columns, well, is equal to the number of column 2 here, and from all these chain of equals are equal to the dimension of row space at the beginning. And then finally we do we get our greater equal sign. Okay, so we got a greater equal sign of we know the dimension of the column space is going to be more than the dimension of a column space. So dimension of column space of A is going to be more than dimension of column space of AL, just because the columns of AL is a subset of columns of A, right? And so you add more vectors to this set, obviously the dimension is going to get bigger. Okay, because you are going to span a bigger space. Okay. Okay. So yeah, so this is what we want to prove. Okay, so I should highlight. So we start with our dimension of our A, and finally it's less or equal to dimension of C of A. Okay, so this is what I want to prove: dimension of C of A greater or equal to dimension R of A. Okay, so this is the hard part, and then the easy part is you do the same argument to AT to transpose of AT, which is the transpose of A. You swap the column and the row, and obviously you swap the row space and the column space. So the column space of AT will be a row space of A, and the row space of AT will be a column space of A. And so you also prove that dimension of a row space of A greater or equal to dimension of column space of A. Okay. So both of those things must be greater or equal to each other, so they must equal to each other. Okay. And yeah, so that's a proof. And about the okay, so the result is important, but so we have something additional, which is that so this process of go from A to U to UL to U to A is actually a pretty useful process, because you find out that it so here in the proof, at this step only know A or is linear independent, but later we know the dimension of A dimension of column of A or actually equal to dimension of column of A, right? Because they are both equal to rank. And so this thing is actually a basis of the columns of A. Okay? Because at the end, we see that they are not only linear independent, they also have the same dimension as the dimension of column space here. So, so and yeah, so this must be a basis of the column space of A. So this whole process, this 4-step process, is actually a way to find the basis for the column space of some vector. Okay, yeah, and yeah, so we now have so the proof step is the algorithm for finding excuse me, for finding the basis for the column space of A. And there's another algorithm that we kind of know that also find the basis. Okay. So if you want to find the basis of the column space of A, you can also transpose it first and find the basis for the row space. And to find the basis for row space, you also do Gaussian elimination. Okay. And remember here, we also find the basis for the row space of A, because so this is the first basis element and this is the second basis element. Okay. So there are two ways. And okay, so there are algorithms to find the basis for the column space of A, or row space of A basically. And but remember, but this is like actually the most useful the most useful two algorithms of this chapter, because basically they are the way to find the basis for if you are given some set of vectors, right? Because a given set of vectors, you can just list them together to form a matrix A. And this will tell you what is the basis for those two vectors, for those set of vectors. And you are thinking about given a set of vectors and list them as columns. And so algorithm 1 will give you a subset of those vectors. See, so here you get a subset of those vectors, and they form a basis. And algorithm 2 will say that, well, you transpose the vectors and list them as rows, and okay, so kind of you transpose the vector and you list them as rows, and you do the Gaussian elimination, and you will find some vectors, and then you see those vectors are not a subset of those, but they are kind of standard because you have those 1 0 0 0 and 0 1. You have these 1 and 0 here, and this 0 and 1 here, so they are kind of standard, although they are not totally standard basis vector, because you have those free variables. Okay, so yeah, so you have two different ways to find the basis out of a given set of vectors, and this also answers a problem that we want to solve in chapter 3.3. That is, how do you find whether your given set of vectors are linearly independent? Oh, I should. Okay. So if you want to find whether a set of vectors is linearly independent, well, you can find the basis and just check whether the number of basis elements equal to the number of vectors you are given. Okay. And so a small review on chapter in section 3.3, we say this. So we have the quadrant of we are given set of vectors, and we want to test whether are linear independent, and we want to solve this formula c1x1 plus c2x2 to ckxk. We want to see whether they have non-trivial solution to some equal to 0, and they write in matrix. So you form a matrix that's listing those vectors together as big X, and you want to multiply some vector c equal to 0. And you found out that you want to test whether they are linear independent, and then you can find the reduced row echelon form of Vx, or row echelon form because you don't need to totally reduce. But anyway, you find the row echelon form of X, and so basically U, and you see whether they have a free variable. Okay. So this is very similar to the process here, right? This is half of the half of the step of algorithm 1. So you list the vectors as column vectors of some matrix, and you do reducer echelon form of this matrix, and so you get something, and you get some lead variable, some free variable. Okay, and you see that if you have a free variable, then the vectors are sorry, I read this wrong. Vectors are not AOI. Okay. So I should say linearly dependent maybe. So if linearly dependent, if they have this equation as non-trivial solution, and that means it has free variable. Okay. And so here you can see from this example. So linear independent means you have free variable, and free variable then you have extra vector in A. Okay. So so that's linearly dependent, and k equal I also read this wrong. Okay. And also is n and is k, and we also see that so some corollary we had before is that when k is equal to n, then there must be variable, and the vectors must be linearly dependent. And and now we see this we can get this in easier way, because if n, then those if k equal to n, then those vectors are in Rn. So Rn is an n-dimensional space, and so we know that there are at most n vectors in n-dimensional space are linearly independent. So if k linearly independent, so if k is greater than n, then they cannot be all linearly independent. So that's algorithm 1, and we see part of it in section 3.3, and now we know better. Okay, and so that's some digression, and finally let's get back to our example. Okay, so example, now we have an example of a bigger matrix A here. Okay, so some matrix A as this, and and then we skip the steps. So hopefully you are all very familiar with doing a calculation to get a row echelon form. Okay. So get row echelon form of A is U, is 1 0 0 minus 2 1, etc. And so row echelon form like this, and we have three lead variable and 2 free variable here. Okay. And so 3 lead variable, and we skip the writing down UL and the AL step, okay? Because we only need to know the location of the lead variable is 1, 2, 5. So we can pick out the first column, second column, and the fifth column of A, and we know it's a basis for the column space of A. Okay. So and we know the columns are linearly dependent because we have 2 free variable here. Yeah. So 1, 3, 5. No, so 1, 2, 5, and they form a basis for the column space of A, and then we know the rank of A equal to 3. Okay. Any question? Okay. And if not, then let's see another example, although it's very similar. So now we have 4 vectors. Okay. And so we can find where are linearly dependent, and we can find the dimension space by them. Okay. So here we are actually given 4 vectors, and so we want to find the dimension spanned by those. Okay. So as we say, any kind of those given vector quadrant can be done by this algorithm. This algorithm 1 or algorithm 2. So you can find where the linearly dependent, and then you can find the space spanned by them, because you can find the basis of them. Okay. And anyway, so we do the same. So we list them together to form a matrix. So x1 here, x2 here, x3 here, x4 here. So we form a matrix, and as usual, we skip the hard calculation part, and we get the reduced row echelon form. So we actually only get row echelon form, because we don't need to get the totally reduced. Okay. So anyway, we get the row echelon form of x, and and is this, and we see it has two Lie variable 1 and 1 here, okay. And yeah, so Lie variable is x1 and x2, so we know x1 and x2 from a basis vector for this, and the dimension of those dimension of the subspace spanned by those four vectors is actually only 2 dimensional. Okay. And let's see, can we see really easy? Okay, yeah, we can see really easy because x3 is obviously twice of x1, and yeah, so x3 is twice of x1, and x4 is, okay, x4 is weird. Okay, x4 is twice of x2, then minus x1. Yeah. Anyway, so our calculation is correct. Okay, and so yeah, as we say, x1 and x2 form a basis, and once you find the basis, you basically know everything about this space. So this space, it has dimension 2, and you know they are not linearly, so and those four vectors are not linearly independent because x3 and x4 can be written as a linear combination of x1 and x2. Okay, any question? Okay, otherwise let's go to the checklist for this chapter. Okay. Okay, and I guess I guess we have 2 algorithms here, right? So we can talk a little more about the second algorithm. Okay. And where it's basically similar. So yeah, so you can view this as an algorithm to find the subspace of the column vectors here. So you have the first column vector is 1 minus 2, 1, 1, 2, and the second column vector minus 1, 3, 0, 2 minus 2, and so you have 4 column vector here. And as we say, the row, you get a row echelon form of A, and you get 3 vectors here. And so you know the dimension of the column. Oh, sorry. Sorry. You have 4 row vectors. So I missed the column and row. Sorry. So you have 4 row vectors here. Okay. So you can see those as the row vectors. Okay. And so so if you are given those 4 vectors, well, maybe as columns, you transpose them into rows. So you have those 4 row vectors, and you can find the basis for the row vectors by doing also the same Gaussian elimination. And so once again, those 3 things will be the basis for the row vectors. And then you see that those are not subset of the rows, but well, they are in a more standard form. Okay. And yeah, so say if you get into reduced row echelon form, then you can easily spend everything inside the row space as those row vectors. Let's go to actual reduced row echelon form example. Okay, so you have a reduced row echelon form here, and say you are given another vector possibly in row space, so like you get like A, B, C, D. And you want to write it as a linear combination of those basis elements, and then you know it's like it must be A times 1, 2, 0, 3. Sorry, wrong notation. Right? You have A, B, C, D, then it must be equal to A times 1, 2, 0, 3 plus C times 0, 0, 1, 2, right? Because on the A register, okay, so A, B, C, D I should also write in this form. Also erase this. Okay, yeah. So this is why I say it's more standard. So if you actually get into the reduced row echelon form, then you can write everything in the row space easily, because A, B, C, D will equal to A times the first first row and C times the second row, because on the first register you have only this 1 on the non-zero thing, and on the third register you only have this 1 on the non-zero thing. So it must be C times 1 here, and it must be A times 1 here. Okay. Yeah, so that's why I say it's a standard. Oh, sorry. That's why I say it's a more standard basis. And yeah, anyway, that's another way to find the basis of it. But I guess the number of calculation is similar. In the end, you are going to find yeah, and I guess here we see the theorem 3.6.6 once again. So so when you run either algorithm 1 or algorithm 2, so you are given set of vectors, you are thinking about you find the basis using either algorithm 1 or algorithm 2, right? And they will give you the same number of elements because yeah, they will give you the same number of elements because when you get the reduced echelon form of either u or ut, you will have the same number of leading variable, and that's kind of come from here. Okay, and yeah, so you can also get the basis for the rows, and by doing the reduced echelon form calculation. And yeah, and in this example, we can think about the 4 different vectors. So we have like y1 equal to yeah. So we can think about maybe this is vector y1, y2, y3, y4, and then we also find that they have those 4 vectors has a 2-dimensional space. Those 4 vectors span a 2-dimensional space. Okay, and so let's go to the checklist of this whole section. So 3.6, we spent a lot of time talking, and we are studying the row space and the column space of a matrix. Okay. And so we have a whole bunch of theorem. Theorem 3.6.1 says that if 2 matrices are row equivalent and they have same row space, and this gives us a way to find the basis for row space, just as we did. So you can find the REF of your matrix, and then the columns will be a basis for your row space. Or if you just get REF, we are also going to get a basis. And the rank is, and then we define those 2 quantities. Rank equal to the dimension of the row space, and nullity equal to the dimension of the null space. Null space was defined before. Null space is the set of vectors that satisfy x equal to 0. And then we see the solution x equal to b can be has some strong relation to the column space. And so we have 2 theorems. First saying that if the system is consistent, so you have either consistence for every b, so you always have 1 to infinite solutions. Considering for every b, so you have 1 and infinite solutions. Then the column spans the whole space Rm. And then we say if everything has a unique solution, so you have a unique or no solution, and you have 0 or 1 solution, then the columns must be linearly independent. Okay. And then from here we have the next theorem, which says you have a square matrix and it's non-singular. So basically, that's from the previous theorem, know that it means it has a unique solution, and that's if only if the columns are basis. So they span the whole space Rn, and they are all linearly independent. Okay. And then we have 2 interesting theorems. 3.6.5, and it's a ring nullity theorem, which which decompose the space Rn equal to the null space and the rank space and the row space. But we haven't studied the decomposition of the space yet. But now we just know that rank plus nullity equal to n. Okay. And then 3.6.6 that we just proved. It says the dimensional row space equal to dimensional column space, and by definition is equal to the rank of n. Okay. And then we have one extra page for the checklist that we talked about. And so we have algorithm that find the basis for for the row space and the null space and the column space. And so you can find all of them by doing just one thing. That is, you do the Gaussian elimination on A, and you find the REF of A. You find the REF of A. Then rows of the U. Then rows of U will be a basis for the row space, and well, the columns of U will not be a the columns of U is not a basis for C of A, but you can, so the thing we have been doing, so you can map the columns of U back to A. Okay. So U is REF, so they are lead variables. So you can find the lead variable in U, then find the corresponding columns in A, and those will actually be a basis for C of A. Okay. And finally, you can find the null space of A. Okay. And it's a bit complicated to write down, but remember you are basically solving Ux equal to 0, and then you have the, okay, so forgot to say, and here you will have the dimension equal to, and remember the dimension of n of A equal to number of free variables. So basically, for every free variable, you will get a basis element, basis vector for this n of A. Okay. So there is a so there is a one-to-one correspondence to one free variable to one basis vector of A. Okay. Yeah, and the thing is a bit more complicated to write down algebraically, but we have seen the algorithm a few times. It's not too hard. Basically, you assume the free variable is something, and you plug it into Ux equals 0, and you get a vector. Yeah. And okay, so that's for 3.6. Any question? If not, then let's go to extra slide, bonus slide. Okay. So this is something we omit a little bit. So I guess this will not. Let's not do this in. We have been skipping those in homework. Although if you look at the text, the book questions, you will see those. They are actually questions related to those two concepts. So there are two vector spaces that I'll kind of skip. That's the polynomial, the set of polynomials, and the set of functions. Okay. And I guess since we are mostly skipping those, so let's not put them in homework. And you already have been skipping them in homework, so let's skip them in homework and exams. So these are extra fun, but they are still interesting concepts. So let's talk about them here, since we have extra time. Okay. And so there are two interesting vector space, and they're interesting because they are very useful in all kind of analysis. So actual math analysis, and and also they are interesting because they are a little weird because they are infinite dimensional. Okay. And so the first example is this vector space of polynomials. So you usually write a P of x, and it's a polynomial x, and usually you need to specify like a scalar here, but you can put different scalar to your polynomials. So your coefficient of the polynomial But since we are mostly deal with real number here, so we just assume our polynomial has real numbers. Okay. Okay. So that's our vector space. So that's polynomial space of arbitrary degree, and they have a real coefficient. Okay. So we can define addition and scalar multiplication. So addition is, so you have a polynomial p and a q of x. Then we define is p plus q, and it's going to be a polynomial of x. It's just p of x plus q of x as algebraic addition. And then we have scalar multiplication. You have alpha times your p of x, alpha times your p, and that's just a polynomial where you multiply everything by alpha. And so here the x is is a bit confusing. So x is not any number. X is an algebraic symbol here. So we think a polynomial as like some coefficient to different degree of x. And so for example, you might have your p of x equal to this 1 plus 2 of x squared. Okay. So yeah, so this whole algebraic expression is one vector. Okay. Remember we are talking about vector space. So this is one vector, and the q of x so maybe equal to -1x, and this is another vector. And so we add those two vectors. So p of x plus q of x, as we say, we just do polynomial addition. So this is a very algebraic manipulation, and so you can add all the terms together and list them together. So it's 1 minus x plus 2x squared. And then similarly, you can do multiplication. So maybe twice p of x equal to 2 plus 4x squared. Okay. So yeah, polynomials, and it's a vector space, and so obviously they satisfy. So so you need to check all the axioms, and they are pretty easy to check. Yeah, you can check all the axioms and see that these rules satisfy all the axioms. And I guess we can see closure easily. So you have one polynomial plus another polynomial. Obviously, you get another polynomial, and you get scalar multiplication. And because alpha is a real number, and so you have a real number multiplying all the coefficients the real numbers. So you get coefficients your real numbers. Okay. Okay. So axioms can lay out. Okay, and then you can think about what's the zero vector here in this vector space. Anyone want to say what's the zero vector here? Okay. And well, anyway, the zero vector is the coefficient all equal to 0. So it's kind of the scalar. So it's just the zero number. So every coefficient is 0 is just 0, kind of the scalar 0. Okay. And okay, and now the basis is a weird concept here because it's infinite dimensional. And yeah, because you have the infinite here, the concept of basis is actually weird. But here we have something that looks like basis. That's all the monomial here. So we have 1 and x squared and x cubed, etc. But well, if you define it this way, then it's weird because we are hiding a lot of infinite thing. And the weird thing is we don't like too much infinite here because then say because you have infinite sum of coefficients, then things can get weird. Let's say this thing actually. So if you have an infinite series 1 plus x squared plus x cubed plus da da da. Then you are summing over infinite number of coefficients, and give people a bit uneasy. Okay, and yeah, so we have a quotation mark on basis, but here I just give you an idea that this space is actually infinite dimensional. Okay? So you can kind of feel, I guess you can prove yourself that yeah, if you have a finite number of vectors inside this space, there are not actually, you can always find the extra polynomial that's not spanned by those polynomials. So this the dimension is infinite is quite provable, but to define a basis, then there are different ways to define basis for infinite dimensional vector space. And yeah, so we're not going into details here, but just know that it's complicated. Okay. And let's see another. Okay, so the next example is this continuous function. Okay. Okay, so we define this continuous function on some interval a and b. I guess we can also define by real line, but we adhere the book example and define them on some closed interval a and b. And once again, we want the real number of scalars, so we have a real value to those functions. Yeah. And so the addition and scalar multiplication looks very similar. So it's a pointwise definition. So f plus g of x equal to f of x plus g of x, and scalar multiplication alpha of x, alpha f of x equal to alpha times f of x. But the x here, the meaning of x here are a little different, although those equations look very similar to those equations. Because here the x we don't need to choose any number. X is just like is just some variable here that to be decided. And but here we think x as some number between a and b because our function is defined on this interval a and b. Okay. Oh, what am I writing here? Okay. And yeah. So a and b can be some interval, maybe 0, 1. Okay. So x is some number between a and b, and we are thinking this. So actually, what we are saying is those two things are for x. So we are having pointwise definition for the function. So for x in a and b, and so we define those two equations, those things like pointwise. So for x in a and b, f plus g of x must equal to those two function values together, and for x in a and b, and this into this is 5. Okay, and so yeah, so we can think about maybe a and b is the 0, 1 interval, and oh, actually let's make this a little easier because I have sin x here, right? So let's say a and b is 0 and pi over 2. So let's make the drawing easier. Then our p of x will be the sin x. So 0 to sin over 2, then sin of x look like this. Right? 0, 1. Okay. And so p of x is this thing. And q of x is minus x, and this thing is 0 to minus pi over 2. Okay, so yeah, so we have those two functions, and we call those two functions as vectors. And so we add them together, and then it's a weird function. Right? So we get p plus q of x is this function and this function, so it's something like this. Is hard to draw, so let's not do that. And then you have 2p of x, and it's just twice of this sine function. Okay, and once again you can check the axioms. I guess you can check the closure. So closure, you need a bit of calculus. You need to say that a continuous function plus another continuous function is still a continuous function. And you need to say continuous function times some real number is still a continuous function. Yeah. And so that's closure, and the other axiom you can check they are satisfied. And so yeah, so once again, what's a zero vector? You want to answer? Okay. And anyway, the zero vector is the zero function here. So zero vector is the thing that anything other than is still and back is still the same thing back. So zero vector will just be the zero function here. So it's constant zero function. It's a zero vector. And now I see the basis is really weird because yeah, how do you find the basis for this thing? Yeah, everything. And then yeah. Yeah. There are really infinite number of things you can say about these functions, and so basis is hard to find. And if you study more math, something like for linear analysis, then you will see some kind of basis thing for this. Yeah, but it's really complicated for those for this vector space. Yeah, so you can check the usual property of vector space is satisfied, but when you want to find a basis, there are a lot of weird things about infinity will happen. And yeah, so for now we just say we know the number of dimensions is infinite. Okay, and yeah, so I guess that's all I want to say today. So we will finish the class early today, and we'll have our midterm review on Wednesday, and yeah, we'll have midterm on next Monday. Okay, so yeah, so see you on Wednesday.